This is the second part of lecture 7 of Logika or računalnistvu on linear time temporal logic. In the first part we did the background, and now in this second part we're going to finally see what linear time temporal logic is. So, as with all the other logics, we're going to begin by introducing the syntax of formulas, and again, as with the other logics, formulas are going to express properties. And just like predicate logic, linear time temporal logic is going to build on propositional logic, but it's going to extend propositional logic in a different way. So predicate logic extended propositional logic by adding variables and terms and quantifiers and things like that. Linear time temporal logic is going to extend propositional logic by adding what are called temporal operators. That's operators talking about time. So that's just, without further ado, tell you what the syntax of the formulas is. So let's say as with propositional logic, we're going to assume a collection of propositional atoms. So formulas are built over a collection. And these propositional atoms are themselves formulas, a collection propositional atoms. So these propositional atoms express like basic properties. So for example, in the mutual exclusion example we considered above, N1 saying that process 1 is non-critical, and T1 saying process 1 is trying, and C1 saying that process 1 is critical, those were all propositional atoms, as were N2, T2, and C2. And then the formulas of linear time temporal logic actually include the formulas of propositional logic. So formulas of LTL are, so the formulas again I'm going to use are given by, so again I'm going to use phi and psi for formulas, and theta and so on. So we're going to have every propositional atom. Actually, let me write it like this. I'm going to write it P. So P is a propositional atom. And let's put in blue every prop atom is a formula. And then if phi and psi are formulas that we've already built, then so are, well, we're going to include all the formulas of propositional logic, so true, false, not phi. Of course, we're not using phi and psi in true and false, and we're not using psi here, but never mind, we can understand what we're doing. We're building formulas from old ones using propositional connectives. So all the constructors of propositional logic. So phi or psi, phi implies psi. So we basically have, we've got the propositional atoms and we have every way of building a formula of propositional logic. So all formulas of propositional logic are formulas of LTL. But then we have the more interesting parts of LTL, which are the formulas built with the temporal operators. So we have a formula written x, a capital X, phi, which you normally write in, if one's writing it in a, one's printing it or writing it in a computer formatted document or a printed document, one uses a sans serif X, here a capital X without serifs, without the little bits of the edges of the letters. I guess that's how one can explain sans serif. Anyway, X phi, this stands for phi holds, this means phi holds at the next state. So let's write the next in capitals to emphasize the X is coming from the next. We have f phi, which we already saw in the formula above, that I wrote above for the liveness property. So this says phi holds at some future state, so f for future, some future state, so it's a sort of existential quantification over future states. And then we have g phi, which we saw in both the safety and the liveness property. And this says phi holds globally, so g for globally, at all future states. And then we have the until operator, phi u psi. So this says phi holds until eventually, put that eventually in brackets, until psi holds. And then we have some variants on until phi w psi that I will explain later. So this is not w here, stands phi holds weakly until so let's make the w, so weakly until psi. Actually, I can tell you, so that's phi holds until either it keeps on holding or eventually we get to psi, whereas the until is saying that we will eventually get to psi. Anyway, you're not supposed to understand this at the moment because I haven't given the semantics, so this will be easier to understand in a moment when we see about how to interpret formulas in a model. For the moment we're just doing the syntax, and there's only one more way of building formulas, that's phi r psi, and this one I really won't explain technically what it means. I just want to explain that, give a word for for the letter R. So this says that the formula phi releases formula psi. What that means we will see in a moment. Okay, so basically propositional logic plus these other ways of building formulas. But of course, once we've got these other ways of building formulas, we can then use temporal formulas and combine them using the propositional connectives. So the propositional connectives are not restricted to the case that the formulas that they combine together come themselves from propositional logic. They can also, those formulas can be temporal logic formulas, as we've already seen, I think, up here, where here we're doing an and, so here we're doing an and the two formulas we're combining are temporal logic formulas because they've got the future operator in, not propositional logic formulas. Also here we're doing a future and here we're doing an implication, and the two formulas we're combining, well, the one on the right is a temporal formula because it contains the future operator. Okay, so that's the syntax. Propositional logic we already understand, fortunately, so we can mainly focus on what these temporal operators mean. So before going into what they mean mathematically, and for that, in order to explain that, we're going to again define a satisfaction relation between, an appropriate satisfaction relation. I want to say something about the interpretation of the temporal logic formula. The idea of a linear time temporal logic formula, as I motivated in the first part of the lecture, is that we're going to look at infinite runs through the system. So a temporal logic formula is going to express properties of what happens during the evolution of the state of a system in a run through the system. And that evolution will be a path through the system, starting at some state and then going to another state and so on. And what we view when we look at the path, we think of the first state in the path as the current moment in time, and the rest of the path as how the system is going to evolve in the future. Of course, it may evolve in many different ways in the future, in which case we'll consider many different paths. But once we fix on a path, we're fixing on a particular evolution through time. And then the first state in the path is now, and the other states in the path are the future. So the second state in the path is the next state, and so on. So in order to define the satisfaction relation, we need to define the notion of a path, or it's also known as a run through the system. So let me say the semantics of LTL. So that's the meaning. So how we understand formulas is specified by defining a satisfaction relation relation of the form maybe that's right. Let's display this more prominently because it's important. Pi, that's a little Greek letter pi, doesn't mean the number 3.1415, etc. It's here it's going to be a run through the system or a path. So we're going to specify a relation pi satisfies phi. Let's write that again. Pi satisfies phi, where pi is a path through a given transition system. So we suppose we've got a given transition system that we're modelling formulas over, and pi will be a path through the transition system, and phi is of course an LTL formula. Phi is an LTL formula. So we should define a path precisely. So before specifying the relation, we need to define what we're talking about. So definition. A path through a transition relation, through a transition system M, is an infinite sequence of transition-related states, as you would expect. So we'll write a path as pi, and we'll also expand it out as, so we'll use S1 for the first state often, and the point is that each successive state must be obtainable from the previous state via the transition relation. Of course, the transition relation is directed, so you can you need to follow the arrow. So the arrows need to point in the right direction. Okay. So that's all the path is. Or sometimes we might call the path a run, every run of the system. We might sometimes consider finite paths as well, but if we don't specify finite, then it means an infinite path. So the default definition here is for an infinite path. And we're going to have some notation. So given a path pi of that form, starting at state S1, so as I said, when I was motivating things informally, we think of S1 as the current state of the system, and pi is as it happens, the sequence of states that is going to result from that we're going to have when we execute the system. Maybe only God knows what that sequence is, but nonetheless we can wrap it up as a mathematical sequence. Okay, so I suppose we're given such a path pi starting at S1, then we define pi supremum I to mean the same run but shifted to start at state Si. So that is the path, the same path that we get, but starting from Si. So i.e. the suffix, if you like, so a suffix of a word is something at the end of a word. This is the suffix or the tail of the path pi, starting from so somehow the point is pi is going to be the whole evolution of the system as consisting of now and the future. So S1 is now and the rest is the future, where we are now. But pi 5, say, if we put I equal to 5, that's going to be the whole future evolution of the future from S5 onwards. So we wait till we shift time by 5, and then we look at the evolution of the future from that point onwards. Okay, so having done this, we can define the satisfaction relation. So let's do that on a new sheet. So we're going to give the definition of what it means for a path to satisfy formula phi. Where we're going to assume that we write that pi is of this form. So we're using S1, S2, S3, S4 and so on as the notation for the states we get in the path phi. So S1 is now, S2 is the next state, and so on. Right, so basically we need to go through every formula instance of phi in turn and explain what it means for the path pi to satisfy that formula. So let's begin with a propositional atom. So we've got the whole run of the system from now and the future. What does it mean that it satisfies propositional atom P? Well, the point of propositional atoms is we're saying they hold now. So at the moment P holds. So for example, if P was in the mutual exclusion example we considered in the first half of the lecture, if P was N1, stating that the system is non-critical, stating that system 1, process 1 is non-critical, then N1 will hold in a path pi if the now state is such that the process 1 is non-critical. So in general, the way of defining that is, well, what we want is we want to check that P belongs to the set of atoms that are used to label the now state, S1. Okay, so when we go back to the definition of a transition system from the first half of the lecture, we have this labeling function, and that tells us which atoms are true at any state. So the set of atoms that are true at any state. And we want to say, does atom P hold now? So we want to say, does atom P belong to the set of atoms that are true at now, which is the state S1, which is the starting state of the path. Okay, so for propositional logic, everything is as expected. So, for example, if we want to check if phi and psi holds in state for path pi, well, that's the same thing as we check that phi holds and we check that psi holds for the path. So conjunction means what we expect. And I'm not going to go over all the other propositional connectives. So, and similar for the other propositional connectives. And let me just say that I have some slides prepared. So if we go here, so I have some slides prepared in which we have all the definition of the satisfaction relation in full. So if you want to refer to that, these will be on the web page for the course. Let's go back to the notes that we're doing. But what I do want to talk you through are the meanings of the temporal operators. So these get progressively more complicated as we go along. So let's go back to black. So the next operator is relatively simple. So the point is the next operator is saying at the next state. Or perhaps a better way of thinking of it is from the next state. So in general, our satisfaction relation is saying a property phi holds along a particular run pi holds along the run pi starting from now. And what next phi is saying is that phi holds along the run pi, but not starting from now, but starting from the next state in the run. So another way of saying that is that phi holds along, well, it's basically the same way of saying it. It holds along the run pi, but starting from the second state of the run pi. So we can use our nice notation here, pi superscript 2, and that is the run of pi starting from the second state. So phi holds starting from the next state. That's what it means for next phi to hold starting from now. So to say phi holds, so F, you might remember, stood for future, and the idea is phi holds at some future state, or really, once again, to be more precise, it would be phi holds from some future state. So for this, we say there exists some future state, and if there's some future state, this is in the run pi, we can count our way to it. So there exists some future state such that phi holds from that future state. Or in other words, phi holds in the run that we get by starting pi from the future state Si. So notice we're including in the future here when in the case that I equals 1, pi superscript 1 is the same thing as pi, because that's just pi starting from the state S1, that's the run pi starting from the state S1, which is the same as the run pi itself. So the future, so really the F operator is saying phi holds either now or in the future. And now the globally operator is rather straightforward, because you might remember that globally means that phi holds everywhere in the future, so we simply say for all futures it holds that phi holds at the future. Okay, so far. We now have 3 binary operators, until, weak until, and releases. So let's do until. So we had phi until psi. So this said that phi holds and continue, or this says that phi holds and continues to hold until eventually psi holds. So to state this, we say that there exists some future time at which psi holds, and up until that time phi holds. So again, like the future operation, we have there exists I greater than or equal to 1 such that, but now we have two conditions. So the first condition is that at this time psi holds, and also the second condition is that until psi holds, phi holds. And we do that by, and also, so phi holds at all times. So eventually psi will hold, but phi is going to hold at all times strictly before the point that psi holds. So we're going to say that every future path pi j satisfies phi for all j belonging to the set 1 up until I minus 1. So a particular case of this, or rather before saying that, so the important things about the until operator is that eventually psi will hold and phi will continue to hold until immediately before psi holds. It does not need to, once psi holds, phi does not need to hold anymore, but phi must hold at all points in time strictly before the time at which psi holds. So a particular case is if psi actually holds now. If psi holds now, then the until operator is vacuously true, as it were, because for I equals 1, we have that psi holds now, and then it does not matter whether, it's irrelevant whether phi holds, because this is the empty set, the I minus 1 is 0, so this set becomes empty, and it's vacuously true that phi holds for all strictly earlier states, because there are no strictly earlier states. Okay, so this is called a strong until because it requires that psi actually holds. We also have the weak until and the releases operation, but I suggest we come back to those at the end of the lecture because already we've gone through rather a lot of definitions of the satisfaction relation. We've got enough to be going on with, so let's make progress now with what we've got, and then we'll come back to complete the sort of somewhat tedious definition at the end of the lecture. So we've got the semantics. Let's go back to our mutual exclusion example. Where is it? Here we are. And let's look at the formulas we wrote. So for the mutual exclusion formula itself, which was a safety property, we said that globally it's not the case that both C1 and C2 hold in the same state. So we would interpret this over any run through the system. So let's start a run through the system, for example, starting at S0. And we take any run in the system, we look at the whole infinite path, and this is simply saying that for that infinite path, so you take whichever infinite path you want to choose, starting at S0 through the system, and it's going to say for the infinite path, then at every state along that path, it's not going to be the case that C1 and C2 both hold. So, as I said, that's trivially true. And now you can refer back to the definition and you see that it is saying what it's supposed to be saying. And again, it's trivially true for the reason that indeed there are no states in the system that satisfy both C1 and C2. Much more interesting is this operation here. So this is saying, if we take an infinite path, we interpret this operation along it. This is saying that it's globally true that so that's at every state, for every state in the path, if T1 holds, then there is some future state at C1 at which C1 holds. And if T2 holds, then there is some future state at which C2 holds. So indeed, we can see that this path does not satisfy this because, for example, let's just get so S1 enjoys the property T1. So S1 enjoys the property T1. And so if we look in this path, there is some state S1 that if we consider the future from that state, so S1 satisfies T1, but the future from that state never satisfies C1 because none of these states satisfy C1. So by referring back, and I ask you to do this, referring back to the definition of the satisfaction relation, you will see that this path does not satisfy this formula. Because to satisfy this formula, whenever T1 holds, there has to be a future state at which C1 holds, and whenever T2 holds, there has to be a future state along the path that C2 holds. So what we can do is we can do the following. We can follow the following procedure if we were designing a system for mutual exclusion. So suppose we had designed the earlier transition system as an example protocol, if you like, for mutual exclusion. Then we could test our model. The idea is that temporal logic would allow us to, we've got the desirable property of testing the model. So we could test the model for liveness by asking is it the case that every run starting from S0 satisfies the formula that expresses liveness. So that was G T1 implies F C1, and T2 implies FC2. Or equivalently, does, so let's call this phi liveness. So equivalently, does the transition system M, which is our safety critical transition system, in state S0 satisfy phi liveness? So here I'm now using the satisfaction relation in a different way, that I'm talking to the satisfaction relation for the transition system and a state. So once we've completed the definition here, we're going to say so we define that what it means for a formula to be satisfied by a given state in a model is, this means, this holds if for every run pi equals S1, S2, S3, and so on, with S1 equals S, we have that pi satisfies phi. So this notation means every run through M, let's say through M, so every run through M from start state S satisfies phi. And we can even also have another notation, just M satisfies phi if and only if. So if we ignore the start state, so just every run from the system from every possible start state. So this is for every run, pi through M pi satisfies phi. So it's quite, so the idea here is the semantics itself, the satisfaction relation, the basic one is defined for a given run. But in general, one's not interested in verifying a property just for a single run, because you do not ever know which run the system is going to have. That's one of the points of such models. The system might take many different, there are many different potential runs. So what we want to do in practice is we want to verify that a property holds. We might know what the start state is, for example. So this corresponds to this version of the satisfaction relation. We know what the start state is, and we want to check that the property phi holds for any possible run. So we want to check if the liveness property holds for any run starting from the state S0. So we submit this to a piece of software that does something really non-trivial. And this thing is called this piece of software is called a model checker. And our model checker looks at the model. This model here is this is our mutual exclusion model. So we submit this property to a model checker, and the model checker tells us that the property is not satisfied. Says no, this property is not satisfied, and it gives us a counterexample run. So it gives us a run that justifies that this property does not hold for all runs. And that run would be, for example, the one we had. We need to go quite a long way back now. This one here, the one that we had before. Oops. Let's mark this. Let's call this star star. So our counterexample run, e.g. star star. Above. The point is, although the counterexample run is an infinite run, because it had a loop in it, it could be specified by a finite number of states. I won't scroll all the way back to it, but you might remember it was S0 goes to S1, goes to S3, goes to S7, goes back to S1, and so on. So it can be specified by a little looping picture. So it's perfectly possible for the model checker to give us such a counterexample. So in that case, we can... So the point is this can be used as a kind of system development method. So we might... So one approach now is we need to improve things because we want liveness to be satisfied. So we might one response is to improve the model. And indeed we can do that. So so let's try and make this as quick as possible. So I won't. So let's start off in again with the same start state. N1, N2, no things are non-critical, so then either of them might become critical. Oh, that's 2. Or and again here we might get to a system in which both. So this is, so now both process 1 and process 2 are trying for the resource. So the picture's looking much the same as before. We're quite constrained in what we can do. Or in this case, once process 1's been trying for the resource, then it could be granted the resource. And then it could be released. Okay. So it could finish using the resource, or while process 1 is critical, also process 2 could try for the resource. So critical 1 and process 2 is trying for the resource. So if T1 and T2 are both trying for the resource, then we could grant access to C1. Now the point here is what we did last time is that when the when both processes 1 and 2 were simultaneously trying for the resource, we allowed that to go either way. We allowed either process 1 to be granted access to the resource, or process 2 to be granted access to the resource. So we had another line down here. But the idea now is we're going to make sure that we do this in a fair way. So we're going to have one state in which both process 1 and process 2 are trying, and we always grant the resource when it becomes available to process 1 in that case. And we're going to have another state here in which process 1 and process 2 are both trying, and we always grant the resource to process 2. So here we go down to a state in which process 1 is still trying, but we grant the resource to process 2. And what we're going to do is make sure that once we've been through this state in which process 1 and process 2 are both trying, and we granted access to C1, we granted access to process 1, next time we get to a state in which they're both trying, we're going to go, well, we want to make sure that we'll get back to this one and we grant access to, so the next time they're both trying, we grant access to C2. So that if we have repetitions of states in which both processes are trying, then the protocol will, in a nice fair way, alternate between allocating the resource to process 1 and to process 2. So let's complete the picture. So here process 2 can go critical. And while it's critical, we can also process 1 can start trying. So we've done everything apart from the important part now. The important part is that once process 2 has been critical while process 1 is trying, then when it gets released, we go to process 1 is still trying and process 2 becomes non-critical. So now that will take us up to here. And notice that by the design of the system, that whatever happens next, process 1 is going to become critical. Because even if process 2 starts trying, we now go down this way, and our scheduler makes sure it makes the fair choice, and now that the processes are trying, it allocates the resource to process 1, because last time it knows that it was process 2 that got the resource. So the point is this. Ooh, that's a little bit too close to there. Let's make a nice line here. So let's again call this S0. And you can verify for yourself. So this model, let's call it M prime, does satisfy, or let's say enjoy, the property, because it's a good property to have. That M prime from state S0 does satisfy our formula phi liveness. So that means along all infinite paths starting from S0 here, it happens that this formula is satisfied. So globally along the path, whenever T1 holds, there is a future state such that C1 holds, and whenever T2 holds, there is a future state such that C2 holds. And as an exercise, let me write it here. it's a very good exercise to convince yourselves of this, because you will get some feel for how tricky the model checking problem is. This is still a relatively simple example, but it's a good illustrative example. So convince yourselves of this. Okay, so if we ask a model checker for the model M prime, it will give us the reassuring answer, yes. Meaning phi liveness is satisfied. So this is a simple example, but it kind of illustrates a process that is really followed in system design, which is you build a system and you check that it has some property that you want. And in this case, we built the system and it did not have the property that we want. So then you redesign the system in such a way that you might avoid that you make sure that the property does hold. Just one other remark about this. So here I'm talking about phi liveness. The point is this formula is stating a liveness property, this particular one, that is relevant to this particular example of mutual exclusion. Liveness is not just this property. So there are many modelling situations in which one is modelling systems in computer science, and in many such situations there are liveness properties that will have some sort of similarity to this, in that they will still be about making sure that something good, it's always the case that something good will eventually happen in the future, but it need not be exactly this property. Here I'm just using phi liveness to mean this property because we're talking about this particular system of mutual exclusion. Before going back to completing the definition of the satisfaction relation, I just want to remark that there might be that there is an alternative approach to liveness here. So an alternative to redesigning the system So if we go back to the original system, and I'm afraid this needs quite a lot of scrolling again. Where is it? Yes, it really does. Okay, here's the original system. You might think, well, actually, this is not such a bad design. So yes, in theory, it might be the case that if process 1 and 2 are both trying, then the scheduler always favours, say, process 2, and so poor process 1 never gets to access the resource. But obviously that's only going to happen with a scheduler that's allocating the resource in a very unfair way. And for most systems that one builds, one would not expect such fairness to occur. So assuming that the processes are allocated in a fair way, then actually this original design is okay, because if things happen fairly, then if process 1 and 2, so if process 1 does try to ask for the resource, then eventually, if there's any sort of fairness at all, eventually, no matter how many times process 2 asks for the resource and tries to get preference, if there's any fairness at all, then eventually process 1 will be granted the resource. So an alternative is to say, well, actually, this is a good model, and we want to explore properties of the model under the assumption that the system behaves fairly. So we can also do that within the context of LTL. So the alternative is, so keep the same system, but assume that it behaves in a fair way. And the idea here is that we can use a formula of LTL to express that the system so to rule out those runs of a system that behave in an unfair way. So we formulate a fairness property in LTL. So e.g., and there are many fairness is quite an interesting subject. There are many ways of formulating fairness properties, but let me just give one rather strong fairness property which is good enough for this particular example. So the kind of fairness property we might want is the following one: GF T1 and T2 implies a conjunction of things. So firstly, GF T1 and T2 and X of C1, and secondly, GF of T1 and T2 and X of C2. So that looks like, as with many things in logic, that looks like rather a lot of symbols, because it is rather a lot of symbols. But in this case, it's actually not that hard to understand. So let's look at GF T1 and T2. So this says globally throughout the run, so at any time during the run, there is a future time such that T1 and T2 holds. So another way of saying that is infinitely often it holds that T1 and T2 holds. And here we've got an implication. And so given that GF says infinitely often, this implication is saying if we have a run on which T1 and T2 holds infinitely often, that conjunction holds infinitely often, then infinitely often along the same run, we have that T1 and T2 holds, and in the next step, process 1 is critical. And also infinitely often along that run, we have that T1 and T2 hold, and in the next step, process C2 is critical. So another way of saying that is, if we have a run in which infinitely often we're in a state in which T1 and T2 are both trying for the resource at the same time, then in infinitely many of those cases, C1 is granted the resource, and in infinitely many other cases, C2 is granted the resource. So that's a very strong fairness property, and that fairness property implies liveness. Unsurprisingly, it's quite a strong property, but the point is that we might want to keep our model, our original model, and explore its properties under the assumption of fairness. So let's call this phi fair. It's a very strong fairness property, as I said. So to test So to test a property of M under a fairness assumption, let's call it the fairness assumption, or our fairness assumption because it's the one we've chosen. There might be other fairness assumptions. Under our fairness assumption, so property psi, let's say, so any temporal property of the system. So we want to check if our system enjoys psi, but we can test that making the assumption that the system behaves fairly. That's the point. What we do is we test the complicated formula. We test that M from state S0 satisfies that phi fair implies psi. So we want to assume the fairness assumption. We only want runs that satisfy the fairness assumption, and it's enough to establish that our property psi of runs holds for the fairness, for fair runs. So in particular, it does hold that our original, so system M here is our original mutual exclusion model, and it does hold that under the fairness assumption we have the liveness property. So we can either redesign the model, or, which was the first way of dealing with the problem with mutual exclusion, or we can implement some assumption about the way the model will behave, for example, some fairness assumption, and prove our property under such assumptions, assuming as long as we can be sure that our assumption is a fair assumption in the reality of how the system is implemented. Okay, so this has been quite a long second half. There is one little tidy thing, one little thing we need to do to tidy up. So this should not take very long now. I just want to complete the definition of the satisfaction relation for weak until and releases. Oops. So the weak until so this holds if and only if either there exists I greater than equal to 1. So this is as for until. Or, so the difference is, in this case, that weak until means phi will hold up until psi holds, but it does not require that psi will eventually hold. So either it will eventually hold, in which case phi holds up until psi holds, as in the strong until, or the other case is simply that for all I greater than equal to 1, well, if psi never holds, then for all I greater than equal to 1, we need phi to hold. So we ask for pi I to satisfy phi. Whoops. Oh, that's a bit messy. That's weak until and releases. So phi releases psi. So for this one, at this stage of the lecture, I need to look at my notes to remind myself what releases means. So let's write it out. So it's not so dissimilar. So it's either, again, let's maybe underline these either ors. So either there exists an I greater than or equal to 1 such that phi holds at I, and for all j from 1 up to I, psi holds at j. So, oh, that should be a j. Or for all k greater than or equal to 1, psi holds at k. So it's sort of like a backwards until. It's now psi is holding until phi holds, but phi does not need to hold, again, like the weak until. But in this case, at the point that phi does hold, psi must continue to hold. So the important thing to notice here is that this is not I minus 1. So this is psi holds up until phi holds, and it still holds at the state that phi holds, after which we're not requiring anything. So we're saying that psi needs to hold until phi holds, in which case once phi holds, from the next state onwards, we've released, hence the release, we've released the obligation that psi needs to hold. If phi never needs to hold, then if phi never holds, then psi needs to continue holding. So the way of thinking of it is phi releases the obligation that psi needs to hold. And just to say that right at the end, some equivalences. Just the so we've included the weak until and the release. So we could omit weak until and release from the syntax. Of LTL, because phi weak until psi is equivalent to phi until psi, or globally phi. And phi releases psi is equivalent to, it's not true, that not true phi until not true psi. So the first one is easy to see, this first equivalence. I ask you to think about it and see it for yourselves. The second one is not easy to see, and it's a good exercise to think about it. So this will really help you understand the semantics of LTL, understanding this equivalence here. I just want to make one remark about it, that here we see that release is defined so using a negation on the outside and negations on the inside. So you can see it's a kind of De Morgan dual. This is like a De Morgan's law for release with respect to the until operator. So release is like a dual of the operator, of the until operator. So I'm going to say exercise to understand this. Okay, well, I feel we've been going on for quite a long time, so I think that's plenty of material for today. So goodbye for this week. Okay, so I'm going to pause the video. Stop. So bye.